This lecture will be over part of Chapter 8, and I've decided to cover electron configuration first. So it'll focus on electron configuration. And the second lecture in Chapter 8 will focus on the periodic properties of the periodic table. Just as a reminder, Mendeleev was the very first person to try to order elements that were known at that time into some type of logical sequence. He did it by the mass of the element. Hopefully you remember that the current periodic table is not organized by mass. It's more organized by atomic number, which is the number of protons. Okay, and so that current periodic table, the modifications were made by a scientist named Moseley. I have a feeling I'm spelling that wrong. Anyway, so Mendeleev was the first one, so he gets a lot of credit for that. And because he saw the repeating pattern when he organized them by their properties, there came the periodic law, which says that when the elements are in fact arranged in order of increasing atomic mass, today in order of increasing atomic number, some properties reoccur periodically. And if you know the periodic table at all, you will know that elements that are organized into the same family or group have similar properties, and so that is the periodic property. All right, back to electron configurations. Hopefully from Chapter 7, you remember that the electrons, according to Schrodinger's model of the atom, which is our currently accepted model, also called the quantum mechanical model, that electrons exist in orbitals, not orbits. They do not orbit the nucleus. They exist in orbitals. What is an orbital? It's a region of space where an electron is most likely to reside. Remember, we can't pin down exactly where an electron is. At the same time, we can pin down its momentum. That was Heisenberg's uncertainty principle. And so we just have this area of space that we like to say that we can probably find an electron. And so we have this notation we use to describe the orbitals that the electrons in an atom occupy. And the notation is electron configuration. It's really kind of a way of saying what is an electron's address. Okay, so just with the 4 quantum numbers and this electron configuration, we can describe the location of an electron and its energy level. And so here's a typical electron configuration notation. So it consists of several parts. The first large number is the energy level, and so since this number is a 1 in this example, it's an energy level 1. It happens to be hydrogen, which is located in energy level 1. S, there'll be a letter then. That letter designates the orbital that the electron is in. It's an S-type orbital. Remember, the SPDF are really sublevels. Okay, and then the superscript is the number of electrons that are in the orbital, in this case an S orbital. And so that's the generic electron configuration. All right, so we also have what we call orbital notation. It's very closely related to electron notation. Orbital notation uses a square to represent the orbital, okay, so just like this, and half arrows to represent each electron. When I say half arrow, the convention is to draw an arrow with just half a head, and that's because each orbital can hold 2 electrons, okay, so every orbital can hold 2 electrons as long as one of the electrons is spin up and the other is spin down. The spin up electron is understood to have a clockwise spin, and the spin down electron is understood to have a counterclockwise spin. Okay, so if you have 2 electrons in an orbital, the spins must be opposite of one another. All right, so here are 3 rules that you need to know before we start electron configuration. I would go ahead and memorize these rules. You may want to jot them down on index cards or however you study for memorization. The first rule is called the Pauli exclusion principle, which is really what I just kind of mentioned. The official definition is that no two electrons in an atom may have the same set of 4 quantum numbers. But an easier way to think of it is that if an orbital holds 2 electrons, they must have opposite spins. Okay? If an orbital holds 2 electrons, they must have opposite spins. So if you were to see an orbital diagram that looked like this, it would be wrong. And if I were to ask you, why is it wrong? What rule does it violate? You would say it violates the Pauli exclusion principle. All right, just a quick diversion before I go over the other 2 rules when doing electron configuration. We have S sublevels, we have P sublevel, and hopefully remember that every P sublevel has 3 orbitals in it. Then we have D sublevels, which have 5 orbitals in them. And then we have F sublevels, which have 7 orbitals in them. Okay? So since an S sublevel can only have 1 orbital, it can only hold 2 electrons. Okay? An S sublevel can only hold 2 electrons. Since a P sublevel has 3 orbitals, and each orbital can hold 2 electrons, the P sublevel can hold 6 electrons. So let me write this down. S sublevel 2 electrons, P sublevel 6. With the same logic, a D sublevel can hold 10 electrons, and an F sublevel can hold 14 electrons. Alrighty. Onward to the next rule. Another of the 3 rules when writing electron configurations, the Aufbau principle. Very simple. It says electrons will always fill the lowest energy orbital available. Okay, lowest energy orbital available. And so helium has, you would look on the periodic table and you'd see that its atomic number is 2, which means it has 2 protons, but also means it has 2 electrons. And you basically need to find a home for each of those 2 electrons using electron configuration. So you start at the very lowest available orbital, that would be energy level 1, and the lowest sublevel is S, actually the only sublevel in energy level 1. And since helium has 2 electrons, this one S orbital can hold both electrons. You can't forget to assign quantum numbers. So just as a quick reminder, if I asked you, and I will ask you, assign 4 quantum numbers to each of the 2 electrons in the helium atom, how would you do it? Well, here are the 4 types of quantum numbers, NL, M sub L, and M sub S. Both of these electrons are in energy level 1. They are both in an S orbital. The L value for an S orbital is 0. So the L values for both of them are 0. M sub L, if L is 0, M sub L must also equal 0. You may remember M sub L can go from minus L up through 0 to positive L. But since L itself is 0, we're stuck with a 0 for M sub L. Now, MS, spin quantum number, which we didn't talk about much, can only have 2 values, plus 1/2 and minus 1/2. So these are the 2 values that the 2 electrons in helium can have, plus 1/2 and minus 1/2. All right, so Hunds Rule is a little bit trickier, not hard, a little tricky to understand, so make sure that you can follow it. Hunds Rule says that if you are placing multiple electrons in a sublevel that has equal energy orbitals, like a P sublevel, has 3 equal energy orbitals. In this case, these are 4 electrons you're trying to place. You want to place the electrons so that they are not paired. Do not pair them up until you have to. So if I were to take these 4 electrons and place them into the p orbitals like this, that would be violating Hunds Rule because I have paired the electrons before I need to. So you basically always want to put electrons in equal energy orbitals as far apart from each other as possible. And that's to minimize the electron-electron repulsion. Alright, so give you kind of a visual of all of the orbitals we're talking about in increasing energy levels. So of course, I'm going to write them out longhand too. 1s is the lowest energy, followed by 2s, and then 2p. 1s, 2s, 2p, then 3s, we're right here, then 3p, then 4s. Now this is what's a little bit odd. If you haven't done electron configurations before, you might think, why are we not going from 3p to 3d? This is just an anomaly that you need to memorize. The 4s orbital is lower in energy than the 3d orbital. This trend continues for every higher level s sublevel. So let's continue. 3p, 4s, then you go back to 3d, and then 4p, 5s, and 4d. So let's take a minute and look at this trend. Everything seems pretty hunky-dory until you get to the 4s. Then you just have to remember that after every higher level s sublevel comes a D. Once you stick the D level in, you go back to the higher energy level 4p. Okay, that happens at every, so you have 5s, 4d. You would also end up with 6s, 5d, okay, and then 7s, 6d. So let's take a minute now and talk about the number of electrons that can go in each of these sublevels. An S sublevel can only hold 2 electrons, so I'm going to go ahead and put that superscript 2 that shows the maximum number of electrons a sublevel can hold. So anytime I see an S, I'm just going to put a 2. They can all hold 2 electrons. Alright, so the P sublevel can hold 6 electrons. Remember that a P sublevel has 3 orbitals, so it can hold a total of 6 electrons. So I'm going to go ahead and put a 6 every time I see a P. Okay? And then, of course, whenever you see a D sublevel, it holds 5 orbitals, and so 10 electrons. So whenever I see a D, I'm going to go ahead and put a 10 by it. All right. So if you don't already have this sequence of energy levels memorized, I would recommend writing it down and memorizing it. You will need to know it to write electron configurations. All right, so onward. Another way to memorize the order of the orbitals is what we call, it's a giant cheat sheet. It's the Aufbau Diagram. It's kind of just a way to memorize. If it confuses you, you can ignore it. But basically, how you create it, in case it'll help you on a quiz or a test, is you write all of the 1s energy levels, starting with 1, moving your way down all the way down to 7. There are 7 periods on the periodic table. And then, of course, there is no, there is no 1p sublevel. That's why that's gone. Okay, so in the second energy level, when you're talking about p sublevels, it starts at 2, energy level 2. Write all of those. Okay, and then the D sublevel does not start until energy level 3, so you write your Ds and then your Fs. Now you have this kind of pennant shape. That's what it has always reminded me of. What do you do? How do you use it? All right, so you want to start, the arrows here kind of show you what to do. You want to start at the beginning and go in the direction of the arrow heads. So the 1s orbital comes first. Then you want to loop around and go back to where you started to the next arrow. Then 2s comes next. Again, we're going to loop all the way back. and whatever you come to is next. So 2p, then 3s, loop back. So remember, you're going on a diagonal here. 3p, 4s, 3d, 4p, 5s, etc. I've written them all down here longhand, so however it's easiest for you to memorize, you absolutely have to have these memorized. So here's a quick summary of the 3 rules before we start electron configurations. Review them if you need to, jot them down if you need to. Alright, so here are the electron configurations of the first several elements on the periodic table. So take a look at them so that you get familiar with what to expect. Hydrogen, the first thing you want to do is locate the element you're trying to write the electron configuration for on the periodic table. Find out how many electrons it has. Hydrogen has 1 electron, and so its electron configuration is simply 1s1. Since the s sublevel can hold up to 2 electrons, the helium is 1s2. At this point, we have filled the 1s sublevel, and you need to go to the next energy level in electron configurations, which is the 2s. So lithium, which has 3 electrons, okay, if it has an atomic number of 3 if you look on the periodic table, so you need to find a home for all 3 of its electrons. Again, you always start with the lowest energy level, which is 1s2, but we need to put that 3rd electron into the 2s sublevel. The 2s sublevel can hold 2 electrons just like the 1s sublevel can, so when that gets full, we need to go to 2p. Remember, hopefully you wrote out the ordering of orbitals: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, etc. Let's look at one of the harder ones. Let's look at sodium. If you were to look in the periodic table to see how many electrons sodium has, it has 11 electrons. So we need to find an orbital to place each of those 11 electrons in. And we're simply going to look at this memorized list of orbitals and start filling. So we end up with 1s2, 2s2, 2p6, and 3s1. If you want to double check that you've placed every single electron that you need to, remember sodium has 11 electrons, count the superscripts. 2 plus 2 is 4, plus 6 is 10, plus 1 more, that's 11 electrons. So we are done. We have placed all 11 electrons that sodium has. So just kind of count your superscripts to keep track of your electrons. Pay attention for a moment to the orbital diagrams that are also on this page, because you do need to be able to draw those. Alright, so I am going to go ahead and show you one rather complex electron configuration, and then on the next slide I want you to try one on your own. So I have shown this electron configuration in every type of notation I can think of that chemists use. Standard electron notation for iron is shown here. You would first look at the periodic table for Fe iron, and you would find it has 26 electrons, and you would simply start writing out the memorized order of orbitals until you have found a home for all 26 electrons. Count superscripts to make sure that you do in fact have 26 electrons. We do. Okay. Be able to write an orbital diagram for this electron configuration. In order to write orbital diagrams, I always write the regular electron configuration first, and then you simply have to remember every time there's an s sublevel, you draw one orbital. These are circles here. Normally they're squares, but don't get hung up on that. The 2s sublevel, again, every s sublevel only has one orbital. Remember, every time you get to a p sublevel, you need to draw out 3 orbitals for every p sublevel. Okay, fill it with 6 electrons as the superscript shows. Notice when we get to the d sublevel, Even if you don't fill up each of the orbitals in the d sublevel, draw a box for them. So even if, let's say, this last orbital in the d sublevel didn't have any electrons, draw an empty box. Okay. Remember Hunds Rule, which says that place each electron into equal energy orbitals individually before you pair any of them up. Okay. And so just take a look at this orbital diagram, make sure that you could reproduce it. Here is the Bohr model of iron also. You can easily, by looking at either the electron configuration or the orbital diagram, you could draw a Bohr diagram. Remember that the large number in front of each part of the electron configuration tells you the energy level that the electrons are located in. So in energy level 1, we have 2 electrons. They're shown right here. Okay. Energy level 2, how many electrons total do we have? 2, 4, 6, 8. We have 8 electrons in the second energy level. And those are shown right here. There are 8 if you were to count them up. On the third energy level, it can possibly get just a little tricky because the energy levels are separated. We have 2 electrons in the S sublevel, 6 electrons in the P sublevel. We've got to skip all the way to here, the D. And this D sublevel has 2, 3, 4, 5, 6 electrons in it. Even though the D sublevel can hold 10 electrons, it doesn't have to. Okay, in this case, there are only 6 electrons to go into it. So the third energy level for iron holds a total of 14 electrons. So you would then begin to draw 14 electrons. So if you count all these up, you would get 14. Okay, and finally, you can't forget the fourth energy level. Iron only has 2 electrons in the fourth energy level. And where's the other one? My little tablet is covering up, but there should be a second electron over here someplace. All right, so let's give you a chance. Lanthanum. I would like you to look that up on your periodic table, find out how many electrons there are, and then I would like you to go ahead and write out its longhand electron configuration. You've got to look back at your orbitals in order of increasing energy. Okay, remember this? You got to do that until you find a home for all of the electrons of lanthanum. When you do that, go ahead and start adding electrons to this orbital diagram until you place them all as you're supposed to, and then finally see if you can draw the Bohr model for lanthanum. So I would strongly recommend putting me on pause. This is very typical of what might likely be a short essay question on your next test. So really, I would like you to challenge yourself, see if you can do it yourself. Alright, so let's see how you did. Hopefully you were able to find lanthanum in the periodic table. It's way down kind of far. Has 57 electrons, atomic number 57. And so the first thing to do would be to write out the electron configuration for lanthanum. And I repeated myself in a couple of orbitals here, which is why I scribbled them out. And so the correct electron configuration is shown here. It ends in 5d1, and if you want to count all the superscripts to make sure that you've accounted for all 57 electrons, once you have the correct electron configuration, you can write the orbital configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, now remember it gets funky, 3d10, 4p6, 5s2, 4d10, 5p6, 6s, these got kind of wonky, the labels. This is really the 6s, 6s2, and then 5d1. Here's the Bohr model. Even though the last electron to go into the lanthanum electron configuration is the 5d1, when you're drawing the Bohr model, you still pay attention to the primary energy level. Since it is 5d, that 5d1 electron is shown in the 5th energy level. And so there are only 2 electrons in the outermost 6 energy level for lanthanum. All right, hopefully you've got that down because we're going to move on. So now it's important to understand there's a real key correlation between electron configuration and the placement of an element on the periodic table. And so we talk about blocks, orbital blocks of the periodic table. The first 2 groups on the periodic table are called the S block. Okay? And that is because look at the electron configurations for hydrogen. It's 1s1. The highest part of the electron configuration for lithium is 2s1. Sodium, if you write out the electron configuration for sodium, for example, it would be 1s2, 2s2, 2p6, 3s1. So when I talk about the highest part of electron configuration, I'm talking about in the highest energy level. The highest energy level configuration of sodium is 3s1. That's what is shown in this periodic table. So take a look at all of the highest energy levels in the electron configurations for all of the elements. If you look down a group, all of the elements in that group share the same ending to the electron configuration. So the first group all end in S1, the second group all end in S2. That's called the S block. The P block, okay, helium's just weird. It doesn't really belong anyplace. The P block, all of them in group 3A end in P1. Group 4A, P2, then P3, P4, P5, and P6. Kind of interesting. Notice also that an S sublevel only holds 2 electrons, so there are 2 groups associated with it. A P sublevel holds 6 electrons, so there are 6 groups associated with P. D block, okay, D sublevel holds 10 electrons, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 groups associated with the D block. Guess how many groups are associated with the F block? Yes, there are 14 groups, just like there are 14 electrons that an F sublevel can hold. All right, so you need to know these blocks. I could possibly give you a blank periodic table and have you circle in and label the blocks. All right, this is just kind of how it looks in summary. The S block, D block, P block, and F block. All right, there are some irregular electron configurations. This might just be like a multiple choice question or two. Typically they occur, well, all the ones I can think of right now occur in the transition metals. And so if you were to look at the electron configurations for, let's say, chromium, all of these are transition metals, and you were to write out the electron configuration that you would expect, it would look something like this. We'll talk about these shorthand parentheses electron configurations later. But for right now, I just want you to look at what you would expect for chromium. But experimental evidence has shown that's not the correct electron configuration. This is. What's happened here? One of the electrons we expect to be in the S sublevel has hopped into the D sublevel. So if you look at each of these comparisons, copper, molybdenum, and palladium, same thing. The expected configuration has a certain number in a D sublevel, but the actual experimentally verified electron configuration has taken basically an electron from the S sublevel and promoted it into the D sublevel. So scientists believe this happens because there is particular stability with half full and completely full sublevels. And so you notice by promoting one of the S electrons into the D sublevel, we now have, in this case of palladium, a completely full D sublevel, and in the case of molybdenum and chromium, a half full D level and a half full S level. So that's particularly stable. So that's just, like I said, probably a random multiple choice question. All right, so you may want to take a break here. I know this is getting kind of long. We've learned about electron configurations. This next couple slides will tell you how to do what we call a shorthand method of expressing electron configurations. You get to the point when you're writing electron configurations where you feel like you're writing two full lines of the symbolism, and so chemists have come up with a shorthand method. And basically what they do, here's the whole electron configuration for sodium, all right? And so what they do is they look at sodium on the periodic table, go to the nearest noble gas before that element. So the nearest noble gas before sodium. So look on a periodic table. You should probably just have one in front of you now. And the nearest noble gas before sodium is neon. And so what we say you can do for the shorthand configuration is, instead of writing out the electron configuration for neon, whatever the nearest noble gas is before, just write that noble gas, in this case neon, in brackets. And then the only thing you have to write out in electron configuration format is what's left over after the neon. So let's try a couple more of those. Let's see, we just did sodium. Let's do magnesium. Again, you should have your periodic table out in front of you. All right, so magnesium, if you look in the periodic table and find the noble gas that comes before magnesium on the periodic table, again, it would be neon. But in this case, in the neons, if you write out its electron configuration, it's 1s2, 2s2, 2p6, okay? So that means that you can take this electron configuration for neon. You don't have to write it. You just put neon in brackets, and the only thing you have to write is what comes after. In this case, 3s2. And so just go down one by one and kind of see what's happened here. All of these elements, and they're all in period 3 of the periodic table, and so they all go back to neon as always the nearest noble gas before them, and then you just write what's left over after neon. All right, go ahead and try this one on your own. This is a more difficult one. This is rubidium. So find rubidium on your periodic table, and the full out electron configuration for rubidium is shown here. So I want you to follow what I just said about writing the shorthand electron configuration. Look for rubidium on the periodic table. Find the noble gas that comes before rubidium. Put it in brackets, and then write the rest of the orbital configuration after that noble gas. And so put me on pause, see if you can do it yourself, and then check your answer. All right, so if you were to look at the periodic table, the noble gas that's nearest to rubidium but still before it in the periodic table is krypton. And if you were to write out the electron configuration for krypton, it would be everything I'm putting in brackets here. This is krypton. And so the only thing not accounted for in the electron configuration of rubidium and that's not the same as krypton is 5s1. So here's the correct shorthand configuration for rubidium. All right. I think this is about the last key topic that we need to cover in this lecture, and that's valence electrons. Valence electrons are defined as the electrons in the highest principal energy level. Okay, remember our principal energy levels go from 1 to 7. Okay, and all you need to do then is, when you're writing electron configuration, look for the highest energy level in your electron configuration and count how many electrons are in it. All of the electrons that are not valence electrons are called core electrons. They're in the lower energy levels. The reason we focus on valence electrons is they determine the chemical behavior. Valence electrons are the electrons that make chemical bonds and make an element reactive or relatively non-reactive. So they're real important. All right, so the number of valence electrons in an element matches up with the group number. So all of the elements in group 1A have 1 valence electrons. This isn't true for the transition metals, only for the A group elements, everything but the transition metals. Elements in group 2A have 2 valence electrons, okay, and onward. Noble gases that are in group 8A have 8 valence electrons, which is considered a full outer shell, which makes an element very, very stable, which is why the noble gases are not very reactive. So pretty much just kind of repeat what I just said. The elements that are in the same group on the periodic table have similar chemical reactivity, and it's because they have the same number of valence electrons. So the alkaline earth metals in group 2A are quite reactive, the halogens in group 7A are quite reactive, and the noble gases in group 8A are what we say inert, pretty unreactive. You can force them to react, but it's not easy. Notice that the last part of the electron configuration for the noble gases is S2P6. Okay? So, in other words, the highest energy level for all the noble gases is 8. So, 2 plus 6 is 8. 2 plus 6 is 8. Okay? So, notice that. That is in common for all of the noble gases. Alkali metals are group 1A. They are the most reactive group on the periodic table. Okay? Very low what we call ionization energies. Very easy to remove that 1 valence electron they have. They all have 1 valence electron. It's very easy to remove, and so they're quite chemically reactive. And because it's easy to remove the 1 valence electrons, what happens when you do remove 1 valence electron, or 1 electron period? You get a +1 charge. And so the alkali metals tend to, when they react, tend to end up with an ionic charge of +1. The halogens are in group 7A. They have 7 valence electrons. Okay, so remember that all of these elements are trying to become noble gas-like in their electron configurations. All of these elements would like to have 8 valence electrons. That's the octet rule, okay? And so really the shortest and easiest way for them to get 8 valence electrons is what they're going to do. Halogens have 7 valence electrons. The easiest thing for them to do to get 8 valence electrons is to just take on 1 more electron, okay? I suppose they could lose the 7 valence electrons they have to get the undershell, the lower energy level, full, but it's a lot easier for them to gain 1 than to lose 7. And so when the halogens chemically react, they tend to gain 1 electron and take on a charge of -1. And so the groups with the charges, first I want you to understand the elements in their natural state on this earth. They're typically neutral. They don't go around with charges. But when they do chemically react and become ions, these are the charges that they almost always assume. Group 1A alkali metals all tend to get a charge of +1. Group 2A lose their 2 valence electrons and assume a charge of +2. Transition metals, all bets are off. They have variable charge. The group 3A elements, when they react, tend to have ionic charges of +3. The group 4A, which is the carbon group, they tend to not want to make ions because it'd be +4 or -4. They tend to just kind of make covalent bonds. Group 5A, they have 5 valence electrons, and so they tend to want to gain 3 more electrons to get an octet, and so they tend to have charges of -3. Oxygen group, group 6A, has a charge of -2, and the halogens, which with their 7 valence electrons tend to gain only 1 electron for a charge of -1. Noble gases don't tend to gain or lose electrons, they remain neutral. If you don't already know these common charges, that is also a very good thing to memorize. Alright, so you do need to be able to write the electron configuration for anions or cations. Okay, anions are ions with a negative charge. Cations are ions with a positive charge. So, for example, look at the sulfur atom. Its neutral electron configuration is here. If I were to ask you how many valence electrons does sulfur have, let's say that you didn't have a periodic table in front of you to cheat, but just the electron configuration. You would look for the highest energy level. In sulfur's case, it's 3. And you would count the total number of electrons in that highest energy level. There's 2 plus 4. There are 6 valence electrons. Sulfur does also happen to be in group 6A. Okay, so you could have predicted it that way. Group 6A elements have 6 valence electrons. They tend to gain 2 more electrons so that they can have 8 valence, the octet rule. And when they gain the 2 electrons, they have a charge of -2. So if you were writing the electron configuration for the sulfur anion, you would have to add 2 electrons to the regular electron configuration. Take a minute, make sure you understand how we got this electron configuration for the sulfur 2- anion. Last slide. Electron configuration of cations. Okay, groups 1A, 2A, and 3A tend to lose electrons and become cations with a positive charge when they chemically react. Magnesium is in group 2A. It has 2 valence electrons. Double check that. Highest energy level is 3. There are 2 electrons in that highest energy level. So when magnesium reacts, it tends to lose the 2 valence electrons it has. So if you were to write the electron configuration for the magnesium cation, this is what it would look like. Just take away those 2 valence electrons. Notice now that the 2s2, 2p6 is similar in electron configuration to a noble gas. Noble gases have 8 valence electrons, and so does the magnesium cation. That's it for this lecture. I'll put another lecture on later on about periodic trends.